4 lectures on relativistic. Yeah, I have 4 lectures on relativistic kinematics. So little bit of detailing I have done, so that is quite useful. But may I know how many are in first year and second year? Again, it will be difficult to know because your raising hand I cannot observe. Since it is a mixture of first year, second year, up to 5th year students, sometimes theory colleagues or students. For few of you, it may sound very trivial, I know it, but few of you may appreciate the new things. So again, my apology to the experts, and I guess the beginners for whom this school is meant for, so they will enjoy. So fine, so let's go ahead. So before I start the usual lecture, so I would always urge that Einstein's the famous statement. Yeah, Siddhartha, just stop me when my time is over. Okay, because I cannot judge my time.
Yeah, I will just inform you around.
I don't want to take Santu's time, so you can stop.
Yes.
Me. Okay. Yeah, so I would urge the students who are next generation scientists and engineers to follow the statement of Einstein. So he defines education is not the learning of facts, but the training of the mind to think. Okay, so when I give a statement, even if it is mathematical or verbal statement, you try to simulate in your mind and try to train your mind to think that way. So then you will have a proper physical realization. So this is my urge, because otherwise these will be statements and some mathematical formula. This is applicable to all subjects. So training of mind is important. And this famous cartoon of Sir Isaac Newton. So you see, apple falls everywhere, but what prompted Newton to think about gravity? So that is what is the training of mind. Okay, so before I go ahead, the material which I am going to cover is part of our ongoing book, which is a bit delayed, of course. So we are thinking to finish by next year. So the relativistic kinematics for beginners, and it has Monte Carlo. So written by me and Professor Basant Nandi from IIT Bombay. So it should be released by next year or so. We are making a proofreading. So most of the materials are from the part of this book. And I gave a lecture in IIT Madras ACRC school. So a small part of it is in this archive. So you can follow this too. And other things which I follow is again this red font. So this is again a Springer lecture note in physics written by some of the colleagues from Germany and me. So mostly I will follow these 3 books or part of the writings. But however, you can find many good books in your library or in internet, starting from Introduction to High Energy Heavy Ion Collisions, which usually people follow C.Y. Wong. So another very good book, more theoretical aspects of particle production and other things are described, Ramona Vogt, Ultra Relativistic Heavy Ion Collisions, and Introduction to High Energy Physics. Porkin is a good book, but not completely our heavy ion physics, but that has good descriptions of some of the kinematics, not everything. And the notations I will be following, particularly 4-vector and other things, are from Griffith's standard. Okay, the metric and other things which I follow is from Griffith. And a very old book on relativistic kinematics is the Hagedron. So it has reprints, it is available also. But it is more particle physics centric compared to heavy ion physics. And there are also books like Introduction to High Energy Heavy Ion Collisions by Cernay, Rafalski and Lattiser. Okay. So let me put a disclaimer, because as Siddharth requested, this video is going to be public. So this presentation is purely for academic training purpose. As you understand, this is Alice India School to train the next generation scientists. And most of the slides are based on our upcoming book given in the reference 1. Many plots and ideas come from excellent textbooks listed on the previous slide. Lots of good material can nowadays be found by just Googling it. Okay, the authors are then not always recognizable or acknowledgeable. Always it is not possible to acknowledge where the materials are taken. So that is why I put this disclaimer. Okay, so with this disclaimer, now I welcome all of you to Geneva, CERN. So this is the beautiful landscape, as you can see. This is just to excite you before I take you to the jargons of kinematics and relativistic heavy ion collision. So this is just to excite you that you are going to work in this experiment, which is based in Geneva, Switzerland. This is the whole landscape of Geneva. As you can see, you will have mountain Jura and Alps, and it is a very beautiful city of Geneva where the CERN is located. Okay, this is the new view of CERN, but I believe that when you come here, so you will find a bridge connecting the left side to the right side. So where the new exhibition is coming up. So this is under construction, but this is the present view. Bearing that bridge is not shown here. Okay, so this is the beautiful view. As you can see, this is the globe, and this is the mountain Jura, which is visual. Okay, and this is part of the excitement that we are going to work, or we are already working in the world's largest accelerator station at CERN. Okay, and this houses many experiments. Broadly, the big experiments are ALICE, CMS, LHCb, and ATLAS. And each experiment is aimed with a different kind of physics, underlying physics to discover. And ALICE has the primary aim of creating the primordial matter of quarks and gluons, which is called Quark-Gluon plasma, which we are studying, and characterize this hot soup of quarks and gluons. Okay, and other CMS and ATLAS, although they have heavy ion programs, so they deal with particle physics research. Okay, and there are, these are big experiments, but there are small experiments as well. Otherwise, small experiment people will complain. I got a small complaint while giving a talk in Wigner. So it is not 4 number of experiments in LHC, there are many more also. Okay. So before I start, let me ask you the question, why high energies? So why do I need to go for so much of GV, TV energies? What is the requirement? To understand this, so in particle physics, we deal with the elementary particles. When I say elementary, the meaning is there is no substructure. They are point-like objects. Okay. And when I say point-like object, the one which looks like a point-like object to me, if I take out my glass, it may not look like a point-like object. I may not see that also. So this also tells me that this definition of point-like is a relative concept. Okay, what I am using to see that, so that matters on the probe. Okay, so this elementariness, as I explained, it depends on the resolution of the probe used to investigate the structure or substructure of the matter. What kind of probe you are using, what is the associated energy, or in other words, is wavelength. So it depends on that. That defines the elementariness at that energy. Okay. Today, as you understand, quarks or gluons are elementary, but tomorrow you do not know if somebody discovers substructure of quark going to much higher in energy. Because I remind you, once atom was also elementary. The word atom is derived from the Greek word atomos, and atomos meaning is it is uncuttable, indivisible. So at one point of time, atom was also elementary in nature with no substructure. So with advent of high energy accelerators, new technologies involving both mechanical, electrical engineering, and for data analysis, computer science and all that. So we are in a domain that, we no longer consider atom as elementary, and we have emerged to a different domain of quarks and gluons being elementary. So the point I would like to make is, so the elementariness, the definition of elementariness depends upon your resolution of the probe. So what energy accelerator you are using. Okay. So assuming the probing beams consist of point-like particles, the resolution is limited by de Broglie wavelength of the beam of the particles. Okay. And this famous formula of de Broglie, for which he got Nobel Prize, which essentially relates the duality. One side it is lambda, other side it is mass of the particle involved. So it is, so that is why this is the duality equation. But the powerfulness is, so this relates to the beam momentum. Okay. So if I have a higher beam momentum, or in other words, a high energy probe, this can probe very low lambda, low length scale. Okay, so pictorially, if I show it, so it will be better understandable by you. Okay, so beams of higher momentum have shorter de Broglie wavelength, and they can have higher resolution. If I have shorter de Broglie wavelength, shorter wavelength can probe deeper into the structure. Okay, so before I come to the picture, so let's take an example. To probe a dimension of warp 1 Fermi, so Fermi is not a strange thing now to us, it is 10 to the power minus 15 meters. Say the inner structure of the nucleon, the charge radius of the proton, we know that it is 0.843 Fermi. Okay, so if I take this as the dimension and try to probe the inner structure of proton, taking this charge radius as the dimension, you will realize, doing a small calculation, which I urge everybody should do at least once to train your brain. So your beam momentum should be around 1.47 GeV. So 1.47 is not important to me. What is important to me is the order of GeV. So the energy required to probe the inner structure of proton with the dimension of few Fermi or 1 Fermi is essentially GeV order. Okay. So this meaning is, so if I want to probe inner structures, so I need lower and lower lambda, the wavelength. Okay. So this is clearly understandable from the famous Nobel Prize winning small and beautiful equation of lambda is equal to h over p. So now with exploiting the same concept with the primary aim to probe this object, which is a red circle here. So I am using a probe, and the probe is defined through the momentum or energy associated with it. And mathematically, I translate that energy or momentum to its wavelength, and wavelength is now this. So you can see that this is a low energy probe because it has a larger wavelength. And pictorially, when I see, and I remind you of my first principle of optics, if I want to see an object, the associated wavelength should be less than equal to the dimension of the object. So as you can see here, it is not that. So I cannot probe the inner structure. Rather, if I have a high energy probe, it has smaller wavelength. Smaller wavelength relates to high energy. So slowly I can see the inner structure, which was not visible in this case for a low energy probe. Okay, I guess this pictorial representation should make it clear, and your definition of elementariness should be associated with the energy of the probe rather than a sacred definition of elementariness. Okay, I guess I could convince you that probing these low dimensions, I need very high energies. So what are the other consequences of very high energies? I remind you again, Einstein's famous formula, for which he didn't get Nobel Prize, but it is very famous formula, E is equal to mc². So I will take a little 1-2 steps ahead to write E is equal to mc² as sum over of mi/ci². Okay, meaning if I have enough energy, I can produce many particles or multitude of particles in the final state, including massive gauge bosons, Higgs, other exotic particles, glue balls, pentaquarks, and whatnot, right? Because I have enough energy, and I started my game with probing the low dimension. So for low dimension, I wanted high energy, and high energy gives me a platform to produce any particle or any mass particles in nature's way, in a natural way. Okay, so I can produce any number of particles in the final state. So I would be tempted to replace E is equal to mc² by adding multitude of particles in the final state by modifying this equation as sum over I mi/c². And you may ask me, why sum? Why not integration? Why, or in other words, if I translate that, why my mass spectrum is discrete, why not continuous? So this is the question you keep in mind. I'm not going to answer, or maybe it has no answer, why the final state particle spectra is discrete in nature. Okay, but let me, without digression, let me go ahead with the necessity of a high energy, and as a consequence, I can produce more number of particles in the final state. And I demand now that the essential mathematical tool to describe high energy physics is special theory of relativity. So please stay with me with my demand without questioning that, okay, why high energy needs a special theory of relativity. Okay, so let's stay for 1 minute. So if you do not agree at the end of my lecture, okay, special theory of relativity is not necessary. So then I have to convince you in different way. Okay. So why high energy physics? Why special theory of relativity in high energy physics? Okay. So in high energy physics, particles are treated relativistically, as we know. And what is the meaning of relativistic treatment of particles? Because energy goes like PC, or it is equivalent to momentum. And the momentum is very high compared to mc², or a rest mass of the particle. So meaning, as you know, the total energy has an inertial component and another kinetic component, right? Inertial is related to your inertia of the body, or the mass, rest mass of the particle, plus the kinetic part. The kinetic part is so high, I can simply ignore the inertial part. So that leads me to the relativistic domain. Mathematically, I am tempted to say that the momentum of the particle is very high as compared to the mass of the particle. This is the domain where I would say that my particles should be treated relativistically. And as I told you, why special theory of relativity, I'm going to justify. Just hold on for some time. So once the kinetic part is very high compared to the inertial part, this also translates mathematically that my velocity of the particle is comparable to the speed of light. So I am in a very high velocity domain. Okay. So when I say particle is relativistic, so its momentum is very high compared to the rest mass, or in other words, its velocity is comparable to speed of light. So it travels with very high velocity. So again, if you want to characterize different particles taking velocity into account, I would say it will be misleading in relativity. So that is why before I establish that fact, so let me define a relativistic factor, which is gamma, and gamma is equal to E over m. So how it is coming, we will know slowly, but let me define and go ahead. So this relativistic factor gamma is E over m, and please note here that when gamma is equal to 1, the particle is at rest. Because gamma definition you must be knowing by now, it is 1 over 1 minus the relative velocity beta square. So if it is at rest, so that term in the denominator is essentially the second term b by c is becoming 0, and then gamma is equal to 1. So particle is at rest. So when close to speed of light, v goes like c, there is no use to talk about absolute velocities. For example, if I say that, okay, my 1 electron and 1 pion of 1 GeV energies, so they are traveling almost at the velocity of light, you cannot distinguish them. Okay, so that is the reason I bring forward the relativistic factor gamma, which will distinguish a 1 GeV pion from 1 GeV electron. Because the mass will be involved here, your gamma factor will be different. Okay, but if you take the velocity, so velocity can be 99% of the speed of light. So velocity is no longer a quantity which can distinguish 1 GeV pion from 1 GeV electron. So I guess the message is clear, or I am going faster. Anyone?
No, sir, it's clear.
Clear. Okay. So if that is clear, so now let's go ahead. What are the caveats? So caveats in special theory of relativity, the space and time cannot be treated independently as is done in Newtonian mechanics. So we are more familiarized with Newtonian mechanics, but I'll just brush upon your memory what are the problems and which way we went ahead to formulate this Lorentz transformations, taking the Minkowski space and treating time and space equally, unlike the Euclidean geometry or Galilean transformation. That is my aim. So space and time they cannot be treated independently the way it was done in Newtonian mechanics and Galilean transformation. If I remind you, considered time as absolute. Okay. So physical objects that were treated as independent three-component vector and a scalar, for example, in non-relativistic physics, mix in high energy phenomena. So they make energy, momentum, time and space. Okay, so they make it one word, like energy momentum is a 4 vector, your space time is also a 4 vector, but unlike in non-relativistic domain, as you know, energy was a scalar, momentum was a vector, and again time was a scalar and space was a vector. Okay, so they combine to form a 4-component Lorentz vector that transforms like a time and space coordinate. Okay, and I again remind you that Einstein was very thankful to Lorentz for giving these transformation equations, which actually helped him to formulate the special theory of relativity. So, so for a consistent and unified treatment, we rely on Einstein's special theory of relativity formulated in 1905, having the following 2 underlying principles. So everybody knows what are the principles of Einstein's special theory of relativity. The principle 1 was invariance of velocity of light. So it is a constant. Velocity of light remains the same, c, in all inertial frames. And the principle 2 says that relativity principle, meaning this requires the covariance of the equations. Physical law should keep its form invariant in any inertial frame of reference. So here I remind you the difference between covariance and invariance. Okay, so try to understand that. So the form of the physical equations, they should be same irrespective of the inertial frame of reference. Okay, and here please take note that the principle of relativity applies to Galilean transformation and is valid in Newtonian mechanics as well. The invariance of velocity of light necessitates Lorentz transformation in changing from one inertial frame to another that are moving related to each other with a constant speed. Okay, so no acceleration. Once the 2 frames are separated through acceleration, so then your inertialness will be broken. So they are connected through constant speed or velocity, so that the frame of reference are termed as inertial frames of reference. Okay, so now to formulate these Lorentz transformations, so let me now talk about 2 frame of references. So consider a Lorentz boost. This Lorentz transformation, I said, is a boost in the x direction. For simplicity, I am making a transformation in x direction, but you are free to go for arbitrary direction. Okay, you will find a nice treatment in our book on arbitrary direction Lorentz transformation. But for simplicity, without complicating the theory, let me go ahead with the transformation in x direction. Although in our experimental setup, you will find my beam axis is z axis. So the transformation will happen in the longitudinal axis or the z axis. So a particle at t, x, y, z is essentially unprimed frame of reference, which is S, is boosted to a prime frame of reference, which is t prime, x prime, y prime, and z prime. And this velocity with which S prime is receding from S is V. And don't again take it as sacred, because when I bring the concept of relativity, you should understand that I am moving, you are at rest is equivalent to I am at rest and you are moving with the negative velocity. Okay. So somebody may consider your lab frame and center of mass frame, or the particle frame and the lab frame in those ways. So you sit in the particle, you are at rest. So to you, the laboratory is moving in a negative velocity. So in that way, this is equivalent to changing to another coordinate frame S prime, which is moving in the direction at a velocity minus v. So S prime moving with a velocity v in x direction, positive x direction, is also equivalent to S prime is at rest, S is moving in the negative x direction with velocity v. Okay. So nothing sacred. These all relativity concepts are actually relative in nature. So you have to understand things properly rather than making it as a statement in the Bible. So let's assume that this S prime coincides with the frame S at time t is equal to t prime is equal to 0. So at the start of the whole game, so S prime was coinciding with S. So the two coordinates, they are related through the following equations, right? So now I am writing the Lorentz transformation equations. I'm not going to derive this because this will be a digression from my discussion. So time, which is the 0th component of my space-time 4 vector, x on which my Lorentz boost is happening, and the transverse components, namely y and z. So they will be always remain same because my boost is perpendicular to this direction, making y and z as transverse components. So then at this point, I should take a note that in heavy ion collision or high energy physics, anything, any observable with a transverse dimension is always easy to deal with because your Lorentz transformation, they are not affected. Okay. So now I am getting a transformation equation for the 0th component and the first component along which my Lorentz boost is acting. So let me define the relative velocity of the particle with respect to c, because c is the highest velocity. So that is the reason, the particle velocity can be weighed with respect to velocity of light. So beta is my v over c. And then the definition of Lorentz boost gamma is nothing but 1 over 1 minus b square by c square is essentially 1 over 1 minus beta square. So always it is easy to deal with matrix. So let me introduce the matrix form of Lorentz transformation. So here in the prime frame relates to the unprimed frame through a transformation matrix, where as you can see this diagonal terms, these are gamma, gamma for the first two. The terms which are remaining unchanged. So this is your y and z, and this will give you the mixing. So that mixing is also not there. Okay. Mixing means the corresponding component you have to see if it is mixed with that or no. So x is mixed with the boost direction is mixed with time. So that is why these are non-zero, this one. And there is no mixing with y and z, that is why these are 0. So you can analyze this transformation matrix in a more rigid way so that you have a feeling of it. Okay. So from these mathematical equations, how this mixing is happening or not happening, which is getting changed, which is not. Okay. Spend little time on this. Okay, so we know there are lots of consequences of special theory of relativity. So namely, immediate consequences are length contraction, time dilation, okay? And if you look at the mass also, the mass m by m0 I am plotting. Now you can see m0 is the rest mass. So when it is 1, it is essentially m0, the relativistic mass increases. And when your beta goes like c, okay, so that becomes infinite. So it has lots of consequences on particle accelerators, because we are essentially going to very relativistic domain of accelerating particles, and your v is almost going like c. That is the reason you will realize the mass of the particle in the acceleration is becoming very high. And I would urge you here that you try to see the skeleton or the schematic diagram of LHC. You will see there are small circles, then the small circles are feeding to the larger circles, and so on and so forth. So the question is why I cannot go for the highest energy directly, why there is a sequential acceleration of small circles achieving some energy and then feed that higher energy to another circle which is bigger than the previous circle. So with this, we go from proton synchrotron and then super proton synchrotron, then LHC. So if you see the schematic of LHC, you will realize that this very principle of accelerating a mass and particles becoming massive with velocity is leading to this sequential acceleration in LHC. Okay. So that you should realize, okay, so this is just a picture or it has some mathematical consequence. Okay, and coming back, the immediate consequences of special theory of relativity is taking those transformation equations. You can verify that there is something called a length contraction. that relates this length L in a moving frame in comparison to length in the rest frame with a gamma factor. Since gamma factor is always more than 1 for a moving particle and it is 0 for particle at rest, so your moving object will be seen from the laboratory as being contracted. That is what you see when you accelerate this heavy nuclei. Those are Lorentz contracted and they look like almond shape, like pancake. Okay. So this is coming immediately from the first observation of special theory of relativity from length contraction. Time dilation is something very interesting. And if you do the derivation, which you might have done in your BSc and MSc days, so this relates to your original time in the rest frame of the particle as gamma multiplied with gamma. So that is why gamma is a larger factor compared to 1. So you say it is a time dilation, unlike length contraction. Fine. And since in the heavy ion collision, you have seen at least pictorially. So there is a contraction along Z direction. My nuclei look like almond shape, that you have seen. But you do not have a physical feeling or mathematical calculation or experimental verification that there is a time dilation. So I'm going to show you, otherwise you will not believe me. Why special theory of relativity? What is the sacredness? Okay. So let me go to the experimental proof of special theory of relativity. So then you will realize, or I can convince you, because I'm assuming that you are starting your research in high energy physics as first year and second year students. Unless I convince you with experimental proof, don't take me granted that, okay, somebody has told me and or it is there in the book, I should take it granted and apply special theory of relativity to high energy physics. Okay, so don't take it granted, just ask question. So in that way, so let me bring a experimental proof. So measurement of velocity and momentum of electron in nuclear radioactive decay. So you take any radioactive source giving me a beta ray at the end. Okay, so if you do that, so let's assume that you can measure the velocity of the beta ray of the electron and the momentum also. So with this, if I plot my P by mv in a non-relativistic domain, your P is equal to mv. So this makes me 1. So if my electron, which is emerging or coming from my nuclear radioactive decay, is a non-relativistic particle, so I would expect that this should be, all the data points should lie on 1. But you will be astonished to see it follows a relativistic equation, and there is a clear deviation from the non-relativistic conjectured line of P is equal to mv, or P by mv is equal to 1. And all experimental data points are falling on the experimental line of the line which is predicted by the relativistic formula. P is equal, P by mv is related through this gamma factor. So P is not equal to mv, it is related through P is equal to gamma mv. So that is the relativistic momentum. So this at the first hand tells me that electron is a relativistic particle from experimental perspective. Let me try to convince a little more. So again, if you look at its kinetic energy, so you can reshuffle this the way I have constructed here. Okay, I have just tried to understand by myself when I saw this equation. So you will start with energy is equal to the kinetic term plus the inertial term, rest mass, and you do a little bit of mathematics, you will land up with P square by 2k is equal to m plus k by 2c square. So if my kinetic term, or in the relativistic domain, your P square by 2k should be m. So since I am taking electron, its mass is 0.55 MeV. So what should happen is, so I should get around mass, electron mass, this line should be there, right? But when I put my experimental data points, what I realize is it is not following a non-relativistic curve, rather it follows a relativistic curve. These are actually experimental measurements. So this tell me that your electron is a relativistic particle, and the relativistic formulated equations involving the boost factor gamma is helping us to explain the experimental data points. So these are in favor of special theory of relativity. So a little more on this. If I plot the kinetic energy as a function of the momentum, the relativistic formula will tell me that this is the kinetic energy is the total energy minus the rest mass energy, and your data points follow the relativistic curve. And in a non-relativistic case, your kinetic energy should have been your p square by 2m, because you write, yeah, the kinetic energy is p square by 2m, but none of the data points are actually following non-relativistic approach. So if you plot kinetic energy versus v over c square also, as you can see, it's good that none of the data points are exceeding 1. So that means these material particles cannot travel with more than speed of light. This is also another experimental signature that c is the highest velocity. And these data points also follow a relativistic curve. Okay, kinetic energy is equal to half mv square is a non-relativistic limit only. Okay, so I think, by this there are enough experimental proofs, at least from a radioactive decay of beta decay in your laboratory, that special theory of relativity is the theory which would be applicable to these subatomic particles. Okay. Okay, so now let me introduce, I don't know, this is, I can actually, I cannot see my title, doesn't matter. So I think I'm talking about proper time. So proper time is because I have not convinced you about time dilation, how it is affecting me experimentally. So before bringing up that, let me introduce proper time. So proper time is the time an observer feels or records in its own rest frame. Meaning, if you are talking about a muon lifetime, it is measured in the muon rest frame only. Okay, so it is like muon is not moving. So that is called the proper time. So my proper time should be measured in my frame of reference. Okay, not your frame of reference, because you may be moving. Okay, and then it will be dependent upon the relative velocity. So the observer's feeling or recording in its own frame, whatever it gives, so that is the proper time. So you have to sit on the particle, okay, then you record the time, that is called the proper time. So you have to keep that in mind. So the proper time is defined as d tau. So when I write definition, so it is 3 bars. So mathematical formula is dt 1 minus beta square, and I demand that this is a Lorentz invariant quantity. Okay, because since I'm measuring in my own rest frame, why it should depend upon Lorentz transformation, which is dependent on the velocity, relative velocity between you and me. So with that definition, I demand that the proper time d tau should be Lorentz invariant quantity. So is my demand correct? I have to convince you mathematically, because mathematics is the language of physics. So let's go to the proof. I start with ds square, which is equal to c dt square minus dx square minus dy square minus dz square. Can you recognize what it is? This is the fourth dimensional length element. And I guess, some of you or all of you may be knowing why the zeroth component is positive and other components are negative. If it's not convincing, I will bring it forward. Okay, just hold on. So this fourth dimensional length element can be now written taking c square dt square common. So then I write this as 1, and then I write in the form of a dt, and this is nothing but 1 minus velocity square, okay, b by c square. So it is 1 minus beta square, and this will be cancelling out or making it c d tau square. Since my fourth dimensional length element is invariant, Lorentz invariant quantity, my right side is also Lorentz invariant quantity. And c is constant, c is a Lorentz invariant quantity. So my d tau is becoming Lorentz invariant. Although to begin with, I started demanding that since it is measured in my own rest frame, this has to be Lorentz invariant. Mathematically, I could show using Lorentz transformation equations, starting with the assumption that fourth dimensional length element is Lorentz invariant, that my proper time is Lorentz invariant. Very good. Okay. And keep in mind that the time measured in my own rest frame is Lorentz invariant. Okay, so keep that in mind. So now let me show you a picture, because my aim is now to show you the time dilation, which is a consequence of special theory of relativity brought forward by Einstein, is important in understanding this subatomic domain or subatomic universe. So if you look at this primary cosmic rays, so they produce hadronic shower, okay, in the atmosphere. So at the end, you get many particles which are produced in our laboratory also, okay. So these cosmic air showers, they produce all the particles which we see in the laboratory. So then you may ask, if everything is produced freely by the act of God, so why I should go to a laboratory? So keep that in mind. Okay, try to have your own answer. We may discuss in leisure. Okay, but without being digressing from my own discussion. So now you try to see that I focus on muons in the laboratory. I focus on the muon decay in the laboratory. How I am getting muons? So those are actually produced in the cosmic rays. That was my aim of showing that picture. Not beyond that, because that picture is full of physics. I don't want to digress. Okay. So the problem one I am giving to you is, you take cosmic ray muons, those are produced as high as 50 kilometers in the atmosphere, okay, and travel towards the Earth at a speed nearly equal to light, let's say, 0.99998 c, without colliding with anything on the way. Otherwise, there can be, little naughty guy saying that, okay, that has collided there. How can I see in my laboratory? Okay, I assume that no naughtiness is involved. So it is directly coming from the upper atmosphere and coming to my laboratory. I have a setup. I want to see if muon decays in my laboratory, or this is reaching here, or it decays in the upper atmosphere. It cannot reach the laboratory. Okay, that is the question in hand. And I am giving you a sacred number, which is muon lifetime. Okay, don't ask me how it is measured now. Just take it as granted. So the lifetime of the muon is 2.2 into 10 to the power minus 6 seconds. Okay, now the question is, consider a pre-relativistic physics. I have no knowledge of special theory of relativity. Question is, would the muons make it to the ground level? Can you see the muons in your laboratory on your tabletop experiment where you put the scintillators, pads for coincidence signal and all that? You can go to VCC, NICER, Tata Institute, many places, this muon decay setups are there. Okay. Now, if you are convinced or not convinced, depending upon your calculation, which actually you are not doing now, neither me. Now answer the same question using relativistic knowledge. Okay, include your time dilation into account. You must see that muons will last longer and they will travel further. They will reach the laboratory. Okay, again, I just put it for reminding. Okay, so take it a home assignment. I would have called one of you to the board and helped you solving this kind of problems, but anyway, it is a virtual world now. So pion decays to muon, and then muon type of antineutrino to conserve the lepton number. And the assignment here is lifetime of pion is much shorter, assuming that the pions have the same speed around 0.998 c, will they reach the ground level? So this is a problem I'm giving in an analogy to the cosmic muon problem. Okay. So still now we are not convinced, do I need special theory of relativity to deal with this problem or no? Okay. Let me try to convince you. So muon decay, this is the equation for muon decay, just, to recall your particle physics knowledge, although it is not used for solving this problem. So in a pre-relativistic scenario, what is the distance traveled by the muon? It is simply the velocity multiplied by the time, right? If your lifetime is 2 into 10 to the power minus 6 second, multiply with the velocity. So let me take the higher side, which is the velocity of light, right? So this is 3 into 10 to the power 8 meter per second. So the total distance traveled is essentially 600 meters. And I have told you that the muon or the cosmic rays produce these muons at 50 kilometers. So this pre-relativistic notion is telling me that the muons do not reach the earth before decaying. So I cannot conduct a muon decay experiment in the laboratory. Fine. But if you see in our daily life, experimentalists do conduct experiments on muon decay in the laboratory. So then what is the gap in our understanding? Because the fact that I observe muons in my laboratory, then this pre-relativistic notion is no longer valid. So the muons must be living longer in the earth frame by a factor gamma, so which I calculate from the given velocity, and I get the gamma factor to be 160. And simply when I use the formula, same formula for calculation of distance d, but the time is modified by gamma t, taking the time dilation into account, the correct distance which the muon travel is 100 kilometers. And I have taken 50 kilometer atmosphere, which is a true value. So this is telling me that the proper time interval in observer's rest frame, delta tau, because time is always an interval, is equal to delta t divided by gamma. So this gamma factor plays a role for us in order to understand the time dilation, which is a special theory of relativity consequence. And in reality, as I explained you through experiment, it is necessary to understand this subatomic domain of the universe. So is it now convincing to all of you that, okay, the kind of entities, the quanta of the system, the particles in the final state I am dealing with, the kind of velocities I am dealing with, I have to use special theory of relativity, Lorentz transformation as a tool. Is it convincing? If it is not convincing, you can raise your hand or say, no, I am not convinced with whatever experimental evidences I gave in last couple of minutes, those are not convincing. If you say that, so then I have to explain it further. Otherwise, if it is convinced, so you take special theory of relativity as the tool to deal with our high energy physics of the subatomic universe. Okay, no questions. So everybody is convinced. Fine. So the fact that muons reach the laboratory in predicted abundances, because we also look at muon flux and we construct our experimental setups. While naive D is equal to VT reasoning would predict that we should not see any, is one of the many experimental tests, as I explained to you, that support the special theory of relativity. Beautiful. Okay, so I think I have time, Siddharth, or I have eclipsed all the time.
Yeah, so maybe if you want, maybe 5 minutes if you have something to show. Otherwise, maybe if you think that this
it is a natural gap. So that is the reason I tried to see my clock. If it is natural gap, I'll stop here.
Okay. Then fine. Then thank you. Okay, so maybe questions. I don't know.
Questions, comments, if it is not convincing, whatever. Yeah, let's see each other. Or maybe you know all these things already, so it is.
Yeah, many of them are, I do not know. Second time.
Yeah, true. Anyway, so little brushing up the mind is always good. So fine. So slowly we'll develop, we'll go to the complicated situation and